When we talk about simple harmonic motion, we are talking about an object which is normally under the influence of two forces. One of these forces is the restoring force, which is what is actually causing the object to repeat the same pattern of motion again and again. In this section, we are going to look at two day-to-day examples of simple harmonic motion. So first, let us start with some assumptions. The first assumption is that in both of the cases that we are going to study, there is no friction, there is no dissipation. This means that the total energy of the system will remain constant with respect to time. The other thing that we have to keep in mind is that the only forces acting here are conservative forces. For example, gravity is a conservative force. The spring force is a conservative force. When an object moves due to a conservative force, its energy will increase or decrease due to that motion, but the total energy of the system as a whole is conserved. So first, let us look at the spring with a mass attached to it. Here we have a simple support. To this support, we have attached a spring, and to this spring, we have attached a mass. And this entire arrangement is resting on a frictionless surface. So there is no loss of energy due to friction when this block moves back and forth. Here, the spring is springy, right? It wants to maintain its original length. If you try to compress it or stretch it beyond that original length, it will try to come back to its original shape, to its original configuration. So if we consider this point to be the point of equilibrium, so if we consider this point here as our reference point, x is equal to 0, any motion to the left or right of this point will cause the spring to either compress or expand. And in both of these cases, the spring is going to generate a restoring force trying to come back to its original configuration, to its original shape. Now, a scientist named Hooke found that the force being exerted on the spring can be given by the relation F is equal to negative kx, where x is the change in the length of the spring. Remember, the length change can be positive or negative, and k is a constant called the spring constant, which depends on the physical properties of the spring. He also discovered that if you had a system where we had a mass m and a spring with a spring constant k, and you gave a small disturbance to the system, the entire system would start vibrating back and forth in simple harmonic motion, and the frequency of this vibration would be given as omega is equal to under root k upon m, where m is the mass of this object, of this block, and k is the spring constant. We know that omega is the cyclic frequency or the rotational frequency, which is also given as 2 pi upon t. So we can say that 2 pi upon t is equal to under root k upon m. If we transpose, we get a new result, that is t is equal to under root m upon k multiplied by 1 upon 2 pi. This gives us the time period for the motion of this block. Another system that we see in day-to-day life which executes simple harmonic motion is a pendulum. So let's consider a simple pendulum. So here again, we have a support and we have a string or cord, and at the end of this cord, we have attached a small weight which is called a bob. The length of this cord can be given as capital L. Now let's examine what are the forces acting on this bob, on this object executing SHM or simple harmonic motion. So we have the force of gravity which is acting vertically down. So here is the force of gravity. The mass of the bob is m. So the force of gravity acting on this object will be equal to m multiplied by g. Now this force can be resolved into two components. So we can say that this force has a component in this direction and a component in this direction, and these two directions are orthogonal or perpendicular to each other. If we use the law of vector projections, this becomes mg cosine of theta, where this is the angle theta, and this is mg sine theta. And mg cosine theta on one end has the other force, the tensile force, the tension in the string acting on the other end. On the other hand, there is no force in opposition to mg sine theta. We will not consider mg cosine theta in this case because it is not exerting any torque on the system. However, we do have a force mg sine theta which is responsible for a torque. And since we can see here that this is a system where this is the arm and this is the force mg sine theta and this length is L, the torque acting on the system tau can be given as negative L mg sine theta. And the reason we have this negative sign here is because this is a restoring torque. What does that mean? A restoring torque is a torque that is trying to minimize the value of theta. Think about it. If you give a pendulum a slight push and then release it, the pendulum comes back to its original position. It is constantly trying to reduce the angle of theta. It is trying to come back to its mean position, but it can't due to the inertia of the bob pushing it further. So here, the negative sign of the torque indicates that it is always opposing the direction of motion of the bob. It is always acting counter to the direction of motion of the bob. We know that the torque of a system like this, since we can see here that this pendulum is actually tracing a part of a circle. So we can notice here that this pendulum, the bob, is actually tracing a part of a circle of radius L. We can say that the torque on this bob, tau, can also be denoted as I multiplied by alpha, where I is the moment of inertia of this system and alpha is the acceleration, the angular acceleration of this system. So we are dealing with a rotating system, so this is angular acceleration. So we have two different results for tau. Let's equate them to each other. So we get a result like this. I alpha is equal to negative L mg sine theta. If we solve this for alpha, we get alpha is equal to negative L mg sine theta divided by I. Now, for small values of theta, if you are dealing with very small values of theta, sine theta is approximately equal. Now, if we consider small values of theta for small angles, the sine of the angle is approximately equal to the angle itself, which means that the above equation can be rewritten as alpha is equal to negative L mg theta divided by I. And this gives us an expression for the angular acceleration of this bob, and it tells us that it is a function of the angle. Since omega is equal to 2 pi divided by t, we can equate the two sides. So 2 pi by t is equal to mg capital L upon I, or t is equal to 2 pi I upon mgl under root. This gives us the relationship for the time period of a pendulum undergoing simple harmonic motion.
Manorama Horizon. Learning made simple.